Welcome to video 3 for lesson 12.3, magnetic force around a current carrying wire. And the first thing we're going to be asking ourselves is, what is the current? It is simply the flow of electrons. Right. Now that is per second, so that is per second, or the units would be coulombs per second. The formula we're going to use with that is I is equal to Q over T. Now Q is the charge in coulombs, and T is the time in seconds, and I is simply just the current, and that is measured in amps. Lightning strike transfers 20 coulombs of charge to the ground in 1.0 milliseconds. We're asked to calculate the current on this. Well, I is equal to Q over T, or plugging in the numbers, that's going to be 20 coulombs per 1 times 10 to the negative 3 milliseconds. Okay, which when you calculate that gets you 2.0 times 10 to the 5 amps, or 20,000 amps. Give this next one a little try here and pause the video. Once you think you got it, come back. Okay, hopefully you got that as being 50 coulombs. Now the next question here is, how many electrons are actually passing in those 10 seconds in this previous question, those 50 coulombs worth? Well, if we take the 50 coulombs, and what we're going to simply do is we're going to multiply that by 1.6 times. Oh wait, sorry. We're going to multiply that by 1 electron as having 1.6 times the negative coulombs of charge. And really that's 50 divided by 1.6 times 10 to the negative 19. But what you wind up with to 3 significant digits is 3.13 times 10 to the 20 electrons that are passing. So that, as you can see, is a whole lot of electrons. Taking a look, the formula that we're pretty much using with all of these is that formula F is equal to B, or force is equal to Bill. Now, there's a little subscript here, M, which talks about it being a magnetic force, and this upside down T just says that the magnetic field is perpendicular to the current in that length of wire. We're not going to be dealing with them where they're coming at an angle or whatnot. Reminder again that the left-hand rule for magnetic fields is going to have a thumb with the fingers wrapped around it. And with the left hand, that thumb is representing the current. And the coils, or the fingers, are going to represent the actual magnetic field around that wire. Now, this is going to, that magnetic field is actually interacting with an external magnetic field in the case of these formulas in order for us to detect them, in which case we'll use the 3-finger rule, where you've got them acting perpendicular to each other. And the left hand, the thumb, shows us the velocity of electrons, or in this case it's going to be the current, the way that the electrons are moving. The pointer is going to be showing us the direction of the external magnetic field. Magnetic field. And then the middle finger, or the palm, is going to represent the direction of the force acting on that wire. So, taking a look at this next example, if a 15 centimeter length of wire experiences a force that's only 0.02 newtons, while 0.7 amps of current run through it. What is the strength of the magnetic field around that wire, or that is going to be encapsulated on that wire? Well, we're going to take that formula, BIL, and really what we're just looking for is the B. So you're going to divide both sides by the current and the length. When you plug in the numbers, times 10 to the negative 2 divided by 0.127 and the 0.15, which is the length of the wire in meters. Note that that was centimeters there. Altogether, you get to 2.10 Teslas of strength. Moving on to one that's a little bit more complicated. Before I do that, we should just quickly note here that we're not worried about the direction. We're just looking at what is the strength, and that's why we didn't worry about the direction in terms of this magnetic field. That more complicated question, 5 or 75 centimeter long wire has a mass of 0.06 kilograms. Really, there should be another 0 there. What is the magnitude and direction of electron flow needed to suspend the wire if in a magnetic field of 0.125 Teslas into the page? So we've got a wire and a magnetic field running into the page. This is my magnetic field, right? So that's representing. Okay, we're wanting to experience a force acting on this, a magnetic force. Now this will have to be equal and opposite to the way gravity works, right? And so the gravity's here. In order to suspend the wire, now if you've got your pointer finger pointing into the page here, and you've got your middle finger pointing up, right, because it's counteracting the gravity, in which case your thumb, which shows the velocity, is this way. And so the direction of the electron flow is going to be to the left of the page, assuming that it's moving up. And now we need to calculate the actual amount of current. And so in this case here, we know that the force is going to be equal to, again, BIL, but that force, magnetic force, is equal and opposite to gravity. So really, I'm just going to substitute an mg for the magnetic force. Excuse me. Now we're looking for the current. We're going to divide by the magnetic field and length, so you've got mg divided by BL is equal to I, and plugging in the numbers, you should get an answer of 5.232 amps. Okay, so hopefully between these 3 videos we have a clear understanding of what's happening with the magnetic field around a current carrying wire.